Okay, so it's time to start today's online seminar. Okay, so the speaker is Seho Park with student, right?
Yeah.
Yes, PhD student of University of Wisconsin-Madison, and he's gonna talking about periodic homogenization of Hamilton-Jacobi equation for infinite system of indistinguishable particles. Okay, please.
Okay. Thanks for the introduction, and thanks all for coming today. And today I'm gonna talk about the periodic homogenization of Hamilton-Jacobi equation for infinite system of indistinguishable particles. Oh, okay. So today I'm gonna talk about the setting of our problem and also about my main result. And then I will explain about the uh, what is the difficulty of the infinite dimensional Hamilton-Jacobi equation. And then I will talk about how to take some advantage from the symmetry of our setting. And of course, this is about the homogenization. So I will talk about the limiting behavior. So it will contain the effective Hamiltonian, effective equation, and also the rate of convergence. Okay, so I will start from the setting. So our infinite dimensional setting comes from the infinite number of particles system. So I'm gonna start from the finite number of particles system. So if we consider the n number of particles on the torus, then the configuration or the position of the particle can be represented by the vector in the space t to the d to the power of n. And here x of I in torus represent the position of each particle. And then the indistinguishability of the particle means the if we relabel the particles, it doesn't change the physical state. So if we have the particle n number of particle x1 through x of n, then for every permutation sigma, then this configuration is same as x of sigma 1 through x of sigma of n. So to describe this system, we can consider the Hamiltonian, which is the function from Rdn times Rdn to R. And due to this periodicity and indistinguishability, so we can say that for every integer vector z, h of x plus z and p same as h of x and p. And also for every permutation sigma, h of x and p same as x of sigma and p of sigma. Okay. And then naturally we can increase the number of particle into infinity. And this setting is based on the work by Gomez and Rebeckian. Uh, so they parameterize the particle labels into the points in the unit cube. Here it is denoted as I, the unit cube, and here I has a Lebesgue measure of the lambda zero. Then the configuration of this infinite particle can be represented in using the map from I to RD. So if we have the map X from I to RD, then X of I represent the position of the particle labeled by I. So in our setting, the state space is the L2 space, the function from I to RD, and this is denoted as free, and this is Hilbert space. So yeah, to describe the dynamics of infinite number of particle, we can consider the Hamiltonian function from V times V, the dual space of V to R. And here V is L2 space, so we can identify the V star, the dual space with itself, V, using the representation. Okay, so that was the setting, and we can encode the periodicity and the indistinguishability to the infinite setting. So for example, for the periodicity, we can consider the integer vector variable functions or lattice variable configuration to space from I to z d. This is denoted as lambda. So the quotient space V quotient by lambda can be considered as an infinite version of torus. And for the real leveling symmetry, we can consider the infinite version of permutation. So for that, we consider the bijection from I to I. So here it is G. So G is bijection of I, and G and its inverse are Borel measurable, and it push forward the Lebesgue measure to itself. It means it doesn't change the size of the measurable set. Okay. So for the bijection here, G, and if we have a configuration X in V, then if we compose by G, X composed with G, represent the real labeled configuration. So those are same physical state. And using those two space, we can encode the symmetry to our Hamiltonian. So similar with the finite dimensional setting, H of X plus C and P is same as X of X and P. So here G is in lambda. And also H of X composed G, P composed with G is same as H of X and P. And G is the rearrangement bijection. And then I want to introduce about the final quotient space. We can quotient V by lambda and also by G. And actually we can quotient a little bit further by certain equivalence class just to remove some degeneracy of the, I mean, it is needed for giving the metric to this quotient space. So this is denoted as SSD, or symmetric infinite dimensional torus. And it has a metric which is the minimum of L2 distance between two functions with any possible rearrangement and translation. Okay. And the good point of this space, this quotient space, is actually it is compact. So if you look at the paper by Gomez and Rebeckian, you can see some lemma about like SSD and its metric is isometric to the Wasserstein space of the probability distribution on the torus with two Wasserstein distance. So it is compact. So SSD is also compact. So we are dealing with the equation on the infinite dimension, V. So it is not locally compact. So as you know, the Radov viscosity argument is the compactest argument, but we doesn't have that. But the good thing is if we quotient by lambda and G, it becomes the compact space. So we have some kind of compactness in our setting. So
Can
I
I
will talk
say,
about it later. Yeah.
yeah, can I say something here just to make a comment? So I mean, like what Seho said, that the SSD with the distance is isometric to W2, right? And actually, there's some other notions that Seho is not talking about here, but basically, it shows that his setting is very natural, because when you have Wasserstadt space, PTD with W2, there's no derivative structures. So the way that people do is that they lift from W2 to L2 anyway, and they define the lift derivative. So this is done by Lyons in the mean-field games framework. That is also used in UC's paper. So, but Seho goes the other way. He goes from L2. So, I mean, in the Hilbert space structure. I just want to explain. Yeah.
Thanks for the comments. Okay, so we explain about the SSD, and this is just a summary for our setting because it is always confusing. So our state space is free L2 space, and then lambda is L2 space to function to integer vector, which encode the periodicity, and G represent the measure preserving bijection of I, which work as a permutation or rearrangement. Okay. And then I will talk about our problem and the main result. So we consider the oscillatory Cauchy problem. So here u epsilon t plus h of x over epsilon and d u epsilon is 0, and this is posed on on V, which is infinite dimensional. And then we will take epsilon to 0 as usual, and hopefully u of epsilon will converge to some function u, and u satisfy some effective equation. with effective Hamiltonian H bar. And also we can talk about the convergence rate of that convergence. And those are the assumptions on our Hamiltonian. So I already talked about the periodicity and the rearrangement invariance assumption on H. And also we assume that H is Lipschitz and H is coercive, but we don't assume the convexity. We assume the general non-convex Hamiltonian. Okay, and then we also have some assumptions on our initial data, which is our initial data U0 only depends on the mean configuration. So here M of X represent the basically mean vector varied function. So it is a constant function valued by the average of X. So U naught of X is same as U naught of M of X. So this is a kind of strong restriction to our initial data, but it will give some symmetric structure to our problem. Okay, so the first result is that the solution of the oscillatory problem U of epsilon converges to some function U locally uniformly, and also use of the effective equation. And the key point of this result is that the limit U only depends on the mean configuration. So what I mean is U of X and T is same as U of Mx and T, or we can say that the limits is only the mean configuration. So it means although we start from the infinite dimension, Cp of epsilon live on the infinite dimension space V, but its homogenized limit U can be governed by the finite dimensional equation. So here everything with tilde is in finite dimension, so U tilde of X tilde and T. So we can define it as U of X tilde chi of I and T. And we can also define U naught tilde or H tilde in the same way. Then the effective dynamics or the dynamics for the limit is actually governed by the finite dimensional Hamilton-Jacobi equation like this. Okay. So that is our first result. And the second result.
Excuse me, excuse me, so what's this chi I? Why this is finite dimensional? Oh, I'm sorry. Yes.
So here.
Chi I is a function. I got you.
Okay, yeah, I just do the dimension reduction because at the end, the limit only depends on the mean configuration.
Got you. Thank you. Sorry.
No problem. So our second result record the convergence rate. So U of epsilon converges to U in the rate of epsilon to the power of 1/3. And this is the same rate as the finite dimensional non-convex periodic homogenization by the Closure-Dorsetta NEC. But the difference is we compare the infinite dimensional object U of epsilon with the finite dimensional object U. And also I will talk later about the corrector. The corrector also live on the infinite dimensional space. And I want to explain just one example of our Hamiltonian. Since our setting is about the particle system, so we can think about the potential on the particle. So here V naught is about the external potential, and W naught is the interaction potential between every possible pair of particles. So here V naught and W naught is periodic, so that's why our Hamiltonian is also periodic. And potential is given by the integral of V naught of X or W naught of the difference between two particles. So it doesn't, it is invariant under the rearrangement. So our Hamiltonian is also have that. And yeah, V naught and W naught are bounded Lipschitz, so our Hamiltonian is Lipschitz. And due to the quadratic term as usual, it makes some coercivity to our Hamiltonian. Okay. So that was the example. And then I want to talk about some introduction about the infinite dimensional Hamilton-Jacobi equation. So in the finite dimension, the most of the viscosity argument need a maximizer of the continuous or smooth function to use the subsolution or the supersolution test. But in the infinite dimension, it is not locally compact. So of course, cross-bounded sets are not compact. So the continuous function on that did not have a maxima. So that is the problem. And we will use two types of two repairs. The first one is something called the Ladon-Nikodym property, and the second one is that I explained before, the compactness of the quotient space SS of D. So the Ladon-Nikodym property, so it is also called as a Stega's variational principle. So the Banach space phi has a Ladon-Nikodym property if for every bounded lower semi-continuous function phi and a closed bow B, then in general, phi need not have a maxima, but for every delta, we can find the small perturbation, which is less than delta, such that if we add that perturbation into phi, then now it attain the maximum or minimum here. So this is called the Ladon-Nikodym property. Not all the Banach space has this property, but the Hilbert space has that. So we can use the Ladon-Nikodym property for our setting. And this will substitute the finding the maximizer that is happen in the finite dimensional argument. So we can just perturb by a small linear perturbation, and then we can just say that we have a maximum, that function. Okay, so for the Banach space with Ladon-Nikodym property, the Krenner and Ryungs developed the viscosity framework for Hamilton-Jacobi equation. So they developed the uniqueness, existence, stability, etc. And also Ishii developed the parents method. It also works on the Banach space with Ladon-Nikodym property. And so based on those work, those well-postness theory, so we have the existence of uniquely exist viscosity solution of our Cauchy problem, and also for our oscillator problem. And I'd like to introduce several related works. I mean, the Hamilton-Jacobi equation on the infinite dimensional setting. So Gamgo and Todorowsko developed some VKM theory on the infinite dimensional torus, and also Gomez and Rubekian. Our setting came from this paper, and they developed the VKM theory on our setting on this setting. And Professor Jin Feng developed some proof about the hydrodynamic limits of the Hamilton-Jacobi equation, and he works on the probability space. And I guess he showed that we can take the limit from the finite dimension to the infinite dimension using the hydrodynamic limit. And recently, the group with Professor Han developed the homogenization theory about the Hamilton-Jacobi equation in Wasserstein space. Okay, and then I will start from the brief review about the parents method. So first we can define the constant, which is the supremum of Hamiltonian with momentum of the gradient of the initial data. Then we can construct a barrier. I mean that we can construct a sub-solution and the super solution of the Cauchy problem, P1 and P2, and then we can construct the envelope. So basically we take the supremum of all the sub-solution between two barriers, P1 and P2. And then the issue shows that this supremum U is actually the viscosity solution. And first it is viscosity when we show the viscosity solution, we need to use the test function and find the maximum of the difference. And then in this step, if we are dealing with the Banach space with Ladon-Nikodym property, then we have to use the Stega's variational property that I explained before. And for the super solution, if we want to show the super solution, it is same as the finite dimensional case. We prove using the assumed by contradiction. So if the U is not supersolution at a certain point, we can just lift that function a bit with some test function and then show that that is a self-solution to make the contradiction. Okay, so and also it should also show the continuity of U, and then U is, and finally we can conclude that U is a viscosity solution. Okay, so the importance of this parents method is, of course, it gives some existence of U of epsilon, and also it gives the Lipschitz regularity of U of epsilon. So U of epsilon is actually Lipschitz in space and time, and that Lipschitz constant is independent of epsilon. So to show this, first, because of the barrier, the time derivative of U of epsilon is uniformly bounded, and from the equation, we have that the Hamiltonian h of x of epsilon and the U of epsilon is also uniformly bounded. And after that, due to the coercivity, we can also say that the gradient of U of epsilon is uniformly bounded. And those constants are coming from the barriers and the coercivity, so those are independent of epsilon. So we have the Lipschitz regularity, equi-Lipschitz regularity of U of epsilon. Okay, so we talk about the Weierposteness of our problem, and then now I will talk about how to use the symmetry of our setting. So first, I'm gonna separate the mean zero functions from V. So here, y is defined as the function with mean zero. Since y is the closed subspace of V, V can be decomposed by y and y perp, and we can easily show that y perp is just a constant function or constant vector variate function, c times chi of I. So every x in V, x can be decomposed by the y part mean zero oscillation and the mean part m of x. Okay, and then we can decompose the y part py of x a little bit further. So I'm gonna approximate py of x into epsilon scaled step function. Here it is denoted as epsilon times z of x. So basically g of x is just a step function with k1. Okay, so because of this approximation, the remaining will be very small. What I mean is the remaining denoted as x of epsilon. The L2 norm of that is bounded by the O of epsilon. And also, since py of x is mean zero, so that's why after some small correction, our epsilon scaled step function approximation that can be mean zero. So what I mean is we can choose z of x, which is mean zero, and also the integer variable function. So here z of x is in lambda intersection with y. So that's why we define the subspace y of epsilon. This is just epsilon times c. C is in lambda and y. So as I talked before, every x in V can be decomposed by the mean m of x and then the epsilon scaled step function epsilon times z of x or y epsilon part, and then the small remaining x of epsilon here. Okay, so the mean part will survive after the limit, and I will talk about how to remove the y epsilon part due to the symmetry, and the small remaining will be absorbed into the O of epsilon error at the limit when on the convergence. Okay, so I will explain about the y epsilon invariance of our solution U of epsilon. So we can just, let's say we translate our equation by y epsilon value or epsilon times z. Then in our Hamiltonian, it becomes h of x plus epsilon times z divided by epsilon. So it is basically x over epsilon plus z, but h is periodic, so it is same. It goes back to our original Hamiltonian. And also, since the initial data only depends on the mean and z is mean zero, so it doesn't change our initial data. So from the uniqueness, we can show that U of epsilon is invariance under the y epsilon translation. Okay. And now we can explain about the convergence. So here, we decompose x into, again, mx, x epsilon, and epsilon times g of x, and that y epsilon part will be cancelled because u of epsilon is y epsilon invariance, and from the equilipsis regularity of u of epsilon, we can compare u of epsilon with its value at m of x using the ellipsis regularity. And only difference is x of epsilon here. So the error is bounded by c times epsilon. Okay? And this will be banished when epsilon goes to 0. So that's why we can restrict the function onto the y perp, which is finite dimensional space equivalent to RD. So if we restrict u of epsilon to y perp, and it is now on the finite dimensional space, so we can use the Majorelli theorems on the compact subset of the y perp times the time space. So from that,
can I ask a question?
sure.
Yeah, do you use some, so you assumed some structure condition on initial data, which depends
Yep.
on mean field interaction. So do you use this condition here?
I used here. So when we show that u epsilon is y epsilon invariant, of course I explained about Hamiltonian doesn't
Okay, I
change,
see.
and also we need
Thank you.
to see that
Sorry.
initial data doesn't change. Yeah. Thank you for the question.
So,
Yep.
in other words, up to this step, can you go back to the previous slides? Of course, the mean condition is natural from the integral representation of the examples, right? But in this step,
Yep.
you only use the fact that it's shifted, but I
Right.
mean, it's for any epsilon, right? So eventually it has to be.
Yeah. Okay, I got it.
Right.
Thank you.
Thank you. Yeah.
Okay, so yeah, we restrict the function into the finite dimensional space, so we have the convergence, and also we have that the limit u only depends on the mean configuration. So basically, we show the half of the first theorem. So now I want to explain about why the limits satisfy the effective equation and what is the effective Hamiltonian. So let's start from the self problem. So here again, the limit u depends only on the mean configuration. So if there's a test function touching u from above or below, then the gradient of that test function is the constant function in y perp. So that's why we can only consider the self problem with the macroscopic momentum at the constant function. And this is consistent with the weak KM theory developed by the Gomez and Durbekian. They consider the self problem of the convex Hamilton-Jacobi equation so that they consider the closed one form on this quotient space, and that is represented as du plus this constant function. So it is consistent with our case.
Excuse me again.
Yep.
Sorry. So this is related to Han's comment. I'm still a bit confused. So by taking derivatives of your functions, you are using those derivative with respect to functions or measures from infield game. Is that the notion you are using? Can you explain a little bit more
Sorry.
what do you mean by taking derivatives here?
It is derivative by the x. So it is Frechet derivative.
Pressure.
So
I see. And
yeah.
somehow you are saying that in the case your function only depends on the mean, then the fractal derivative commutes, or I don't know, with the classical derivative. Is that what you are talking about?
Oh, so here d of phi is the constant function because u changes only in the mean direction. It doesn't change in other directions. So it cannot have
So in this case,
the derivative validation. Yeah.
the Fresher derivative becomes the classical derivative.
I
I
think
see.
so. Yeah.
I see. Thank you.
Yeah, I think Seho explained it here and it's a closed form, but when you go to the next slide, you can also explain to people where the invariance property comes in, because this subproblem is very confusing, I must say, you know. Yeah, so.
Yeah, of course, I will explain about the subproblem. I mean, the invariance of the subproblem. So that's the reason why we can only consider the subproblem with p times chi of I, not the general function in V. So this is our subproblem, h of y and p chi of I plus dv equals to some ergodic constant c. This is posed on V. And then, as usual in the finite dimensional argument, we start from the vanishing discount problem. So we add the monotonicity using lambda times V of lambda. So we have a discount problem like this. And then hopefully, and of course, because of the monotonicity, we have a unique viscosity solution V of lambda. And hopefully, when lambda goes to 0, then negative lambda times V lambda at some point converges to the ergodic constant, and that will be the effective Hamiltonian. And V lambda minus V lambda at some point converges to the corrector. But in the infinite dimension, we don't have the Argyll-Asker theorem, so we cannot argue that there's a subsequence of lambda, something like this. So that's why we have to use the compactness of the quotient space as S of D. So I will talk about how to descend our function to the quotient space. So first, let's say we translate our equation by z. Z is in capital lambda, which is the integer vector variable function. So then, as you can see in the first line of the equation, it goes back to our original Hamiltonian due to the periodicity of h, right? So, due to the uniqueness of V lambda, we can say that V lambda is invariant under the lambda translation. And we can do the same thing for the rearrangement. So if we plug in y composed with g instead of y into our equation, the Hamiltonian looks like the left-hand side in the second equation. Then here we have a constant function, and because we have a constant function that is invariant under the permutation, so we can change that into P composed with G. And then due to the chain rule, and also due to the rearrangement invariance of our Hamiltonian, it goes back to our original Hamiltonian equation. So that's why, because of the uniqueness, phi lambda is invariant under the rearrangement. So that's why we can descend our function V lambda to the quotient space as S of D. And although V is not locally compact, but V lambda is now on the compact space. So that's why we can use the Argyll-Asker theorem. So we can, we can also find the bound for lambda times V lambda. And also coercivity gives the bound for the gradient of V lambda. And this gives and then we define W lambda, which is 3 lambda minus 3 lambda at some point, at some reference point. And also, since the SSD has a finite diameter, so that's why W lambda is equibounded and equicontinuous, so that we can use the Argyll-Asker theorem there. So there exists a subsequence of lambda, which make like negative lambda V lambda converges to C, and W lambda J converges to the solution of the corrector problem. So we just show that the existence of the ergodic constant and the corrector. And same with the finite dimensional case, we can also show the uniqueness of the ergodic constant using the comparison test, comparison argument. So we can define the effective Hamiltonian, and that is only defined on this constant function for y part. Okay, so, and also we can prove that h bar is coercive, continuous, and also Lipschitz. Actually, the proof of this is exactly the same as the finite dimensional case, because our quotient space SSD is compact, which is kind of correspond to the torus. So basically, we can find the maximizer of the corrector, and using the subsolution test, we can show the inequality that H bar is greater than the Hamiltonian at that maximum point, and due to the coercivity of H bar is coercive. And also, due to the stability and the uniqueness of H bar, we can also show the continuity, and also we can show the Lipschitzness from the comparison test between two discount corrector. Okay. After that, I will talk about the effective equation. And once we show that U solves the effective equation with that effective Hamiltonian, and in the previous slide, we just showed the H bar is coercive and continuous, so that's why the limiting equation will be finite dimensional and then well posed. So that will conclude the convergence of whole family of U of epsilon. So okay, let's explain how to show that U solves the effective equation. Okay, so we're gonna use the Evans perturb test method. So it's the corrector of the cell problem. And again, for the viscosity subsolution test and the supersolution test, we need a maximizer, but we don't have that in the infinite dimension. So we're gonna use the Radon-Nikodym property or the Segal's variation property. So first we can think about the test function, which touches U from above on this bounded domain. And then since U only depends on the mean configuration, so the gradient of this test function is in Y perp. It's only the constant function, so we can find the corrector, or we can find the solution of the cell problem is that momentum. Okay, and then we double the variable as usual. So we define the function b, which is U epsilon minus phi minus epsilon times v of y. We separate the fast variable y, and we also add the penalty term, so which couples y and x over epsilon, so they are cross each other. Okay. So first of all, I mean, in finite dimensional case, we just directly find the maximizer and then do the subsolution and the supersolution test. But in infinite dimension, we don't have that. So first, we have to think about the sequence which converges to the supremum of our function phi. So these are xn, yn, and tn. And from this assumption, this inequality for the sequence, we can also say that xn over epsilon and yn, I mean, two vast variable in terms of sequence are close each other too. And also those are bounded, and we can make sure that those are stay away from the boundary, because we just want to deal with the interior to do the subsorption and the supersorption test. Okay, so before using the Radon-Nikodym property, we need to localize near the sequence. So here S of n is the bow with radius gamma centered at xn, yn, and tn. I mean, the centered at the sequence, and it has a radius gamma. And then I'm gonna set delta of n, which is the supremum of phi minus phi at the sequence. Since the sequence converges to its supremum, so delta of n converges to 0 when n goes to infinity. And then I'm gonna add the quadratic penalty at our function, at our double variable function. So psi of n is defined as phi minus those quadratic penalty. So this penalty does nothing at the center, because if x, y, t are xn, yn, tn, this penalty equals to 0. But if you move on to the boundary, it pulls the function down, and on the S of n, those penalty moves at most 2 times delta of n. And because delta of n is difference between supremum and the function at the sequence, so finally we can say that we have a margin between the center and the boundary, and that margin is greater than delta of n. And this is useful because if we need to add the perturbation to attain the maximizer, and then if we add, and then if that perturbation is smaller than that margin, then it guarantees that maximizer happens at the interior of S of n. So that's why we need this kind of quadratic penalty. So as I told, we have to use the Radon-Nikodym property so we can find some small perturbation. We're gonna use the linear perturbation, so Pn, Qn, and Kn for x, y, and t, so that after the perturbation, we can obtain the maximum, and those perturbations are pretty small, so that those maximizer happens on the interior of S of n due to the quadratic penalty that I explained before. Okay, so we have a maxima, xn hat, yn hat, and tn of hat, so that we can use the sub-solution test and the super solution test. So it looks similar to the result from the finite dimensional proof. So you can see the common term in the Hamiltonian, which came from the initial penalty. But we have some extra terms coming from the additional quadratic penalty and also from the perturbation when we use the Radon-Nikodym property. But as you can see, those terms have the delta of n, which goes to 0 when n goes to infinity. So if we take n goes to infinity, those extra terms are vanishing. Okay, and after that, we can take gamma goes to 0, which means we shrink the localization near the sequence. And also we can take epsilon to 0 to make u of epsilon converges to u. So after taking those limits, we can achieve that those maximizer xn hat and tn hat converges to x naught and t naught, which was the maximum the maximizer of the u minus phi, u minus the test function. So we can just subtract two inequality and take those limits to conclude that we have the sub-solution inequality here. Okay, I just explained that U is the viscosity sub-solution, and then the same way we can show that it is viscosity super-solution. And I also explained that H bar is coercive and continuous, so that our limiting equation, our effective equation is finite dimensional and well-posed. So that's why the limit is unique, so that we can conclude that U of epsilon converges to U. I mean, the whole family of U of epsilon converges to U. Okay, that's all for our first result. And then the remaining part is about the convergence rate. I will briefly explain about the sketch of the proof. So first, we can make the estimation of the discounted corrector V of lambda. And again, V of lambda is descent to the compact space SS of D. So we can find the estimation of V lambda, such as lambda times V lambda is Lipschitz momentum, and then negative lambda V lambda and H bar are across each other. And it is identified when lambda goes to 0. So those are the estimation for the discounted corrector, and then those proofs are analogous to the proof by the Ishii, Brusetta, and Capuzzo. Correct? So we consider the doubled variable function. So we subtract, it is u epsilon minus u minus epsilon times v of lambda, and also some penalty terms. So as you can see, we compare the infinite dimensional object u of epsilon and then the finite dimensional object U and also infinite dimensional object V of lambda. So here X is in V and Y is in Y perp. And also V lambda, the set problem only define on the when the momentum is the constant function. So that's why you can see the mx minus y divided by epsilon to the beta. And also that's why we make the penalty term couples the mx and y. And as usual, we set lambda equals to epsilon to the power of zeta. And then later we will optimize the parameters like beta and zeta. So from now on, we will do the same thing as we did in the effective equation. So we will separate the, we have to separate the fast variable and then find the sequence converging to the supremum and then localize near the sequence and then do the perturbation to find the maximizer. Okay, so after those steps, we will have those two inequality. And the middle terms are the extra terms coming from that extra penalties and the perturbation kind of thing. Okay. But the point is, if you subtract them, we have the inequality like 2 times k divided is less than equals to, it is bounded by epsilon to the zeta and epsilon to the 1 minus zeta minus beta. And now we can optimize those parameters. So if we choose zeta and beta equals to 1/3, and if we choose k sufficiently large, then it makes the contradiction so that the maximum happens at the initial time. So that's why we can compare the U epsilon and U using the initial data and also using the estimate of the discounted corrector. Okay, so after that, we will achieve the convergence rate epsilon to the power of 1/3. Okay. So this is the sketch of the proof of the convergence rate. And that's all for my talk. And for the summary, I talk about the Hamilton-Jacobi equation, possibly non-convex Hamiltonian on the infinite dimensional space free, but we need some symmetric structure such as periodicity and the rearrangement invariance of Hamiltonian, and also we need the assumptions on the initial data, which is that U naught only depends on the mean configuration. So based on those assumptions, we achieved the qualitative and quantitative homogenization. U epsilon converges to U, and importantly, the limit U is actually finite dimensional object, which solves the effective finite dimensional effective equation, and the convergence rate is epsilon to the power of 1/3. And then to handle the problems of the infinite dimension, we use the Radon-Nikodym property and the compactness of the quotient space as SFD. Okay, I think that's all. Thank you. Thank you for listening.
Okay, so thank you for your very clear representation. Okay, so is there question, comment?
Can I ask a question?
Yeah.
So, it seems that it's really crucial here, or several techniques you apply that the limit is infinite dimension, but this might not happen if the initial data is not. So, can, if the initial data is not, do you think you can say something here, or what do you expect?
I expect that we at least need some kind of assumption on initial data. I mean, for general initial data, I think we cannot govern the homogenization.
So maybe for general initial data,
maybe we
maybe
can.
there's no homogenization.
I think so, but
Oh.
I have to think about it. But at least we can weaken the current condition a little bit. But I'm still thinking about it.
Thank you. Oh, I don't know, but do you think maybe there's no homogenization, but in the long run, say maybe when time is super large, maybe they converge to the finite dimensional case? I don't know. Just be I'm just guessing.
Hmm.
Okay, I don't know.
I don't know either. Thanks for the comments.
Yeah, I mean, what you said is right, Paul. This is one of the biggest questions that Seho has been thinking about. I mean, he has been also discussing with me, and also when Lovon, Nuber, Kian, and others visited, they also asked the same questions.
Mhm.
Can you go back to the slide when you use the invariance property, Seho? Yeah, I just want to say a little bit about that. The cell problem. Yeah, yeah, this one. So like what when Paul asked, right? I mean, when Seho has that the limit is finite dimensional, then when you take the gradient of a finite dimensional function is a vector, right? So that suggests that Seho that he only need to consider the cell problem for constant function, which is a vector, right? P times the characteristic function of the unit cell, P times G of I. But you can also see it from a very technical level here that I think, for example, Seho is using this property. I'm highlighting it here, that that when you do compositions with any measure preserving map, you need the function to be invariant, right? And the only function that is invariant in this technical level is constant function. So that's why the cell problem is only defined for constant functions. But who knows, right? I mean, I think that it is absolutely true that one needs to understand the general setting.
I see. Thank you.
Actually, can I ask about the condition on the initial data, right? Like you assume that the initial data depends only on the mean.
Yep.
Is it like this is pretty like strong assumption, right? Like basically the function u is then constant. Like it depends only on the diagonal, right? The
Yep.
the RD diagonal, so the d-dimensional diagonal, and like everything else in all other directions, it's just constant, right?
Yep.
So like, isn't this basically reducing it to like a finite dimensional problem from the start?
Oh, so we cannot reduce the dimension at the oscillatory problem
Mm-hmm.
because infinite dimension has an infinite number of directions, so it also have some direction which is not on the main direction. So we cannot reduce
Right,
our
so that you have the
oscillatory
oscillations in the
problem.
other directions as well. I
Yeah.
see. But like, right, so from this, I guess then you end up with the finitely dimensional limit problem, right?
Yeah, at the end, yeah.
Yeah, like the
Yeah,
language is good.
I think along Norbert point, this is also what we learned, right? I mean, I'm learning a lot on this through Seho because I have never worked on this, but it's fun.
Mm-hmm.
That when you consider an infinite system of particles, that they are indistinguishable, right? So what do you want to capture? The easiest thing to capture is that you forget totally about their positions. You only capture about the motion of the mean. I'm sorry, of the center of mass of the system as time goes, right? So this equation of Seho is exactly capture only the motion of the center of mass. And indeed, the initial data forgets everything. It's only remembers the center of mass. So that's why homogenization and reductions of dimension is really beautiful. Now you can keep track with more of the thing, right? By keep track with the second or third momentum, whatever that means. I think it's totally reasonable, right? That is totally open. But I think it's the next thing to do. I mean, it's really important. What happens if you keep track more with besides the center of mass.
So the expectation is if you allow more freedom, for example, the first order moment, if the initial depends on more parameters but still finite dimension, maybe there is still homogenization. That's what you mean.
I think
But
so.
Yes, maybe, and it will, yeah.
Yes, I think so, but maybe I'm wrong. If you don't put any assumption, if it depends on the whole cascades, right? Then I think there's no homogenization. But if it only depends on some moments, then I think so, you know.
Mhm.
It's very deep. I think it's very deep, you know.
Mhm.
Okay, so if there's no other question, let's thanks Seho again.
Thank you.
And yes, maybe we can chat informally.